The hits keep on coming with NASA's James Webb Space Telescope. According to the latest update, the telescope has just discovered not one, but two of the earliest and most distant galaxies ever seen, continuing to break the records it previously set. The furthest galaxy, JWST 14-0, is seen as it was a mere 290 million years after the Big Bang, existing at least 100 million years earlier than the previous record holder. That means that if the universe is 13.8 billion years old, it means we're observing the galaxy when the cosmos was only 2% of its current age. And the light James Webb saw from this primordial galaxy has been traveling for 13.5 billion years on its way to reach us. What's interesting, JWST 14-0 isn't alone either. It was discovered along with another galaxy, JWST 14-1, that is almost as far away and takes second place in the ranking of the earliest galaxies ever seen by humanity. The announcement of the discoveries is the latest development in the ongoing investigation of cosmic dawn that the $10 billion telescope has facilitated as part of the JWST program. JWST aims to provide vital insights into the ways in which the stars, gas, and black holes were evolving in primordial galaxies when the 13.8 billion-year-old universe was very young. According to team member and Kavli Institute for Cosmology scientist Francesco Dugenio, these galaxies join a small but growing population of galaxies from the first half-billion years of cosmic history, where we can really probe the stellar populations and the distinctive patterns of chemical elements within them. But JWST 14-0 isn't just remarkable for how distant it is from Earth and how early it existed in the cosmos, though. With a width of around 1,600 light-years across, this cosmic dawn galaxy is also remarkable for how big and bright it is. The extreme brightness of JWST 14-0 and the fact this luminosity is powered by young stars means this galaxy represents the most striking evidence for the rapid formation of large, massive galaxies in the early universe found thus far. JWST team member and University of California, Santa Cruz researcher Ben Johnson added that JWST 14-0 shows that galaxy formation in the early universe was very rapid and intense. The Webb telescope is adept at seeing early galaxies thanks to the high infrared sensitivity of its instruments, particularly its primary imager, the near-infrared camera. Light leaves these cosmic dawn galaxies with a wide range of wavelengths, similar to light from galaxies that are closer to the Milky Way. It is the journey of billions of years that transforms this light into low-energy and long-wavelength light in the near-infrared and infrared regions of the electromagnetic spectrum. The very fabric of space is expanding, and as light passes through it, its wavelength is stretched along with it. This causes the light to shift down to the red end of the electromagnetic spectrum, hence the name for this phenomenon, redshift. Galaxies that are farther away have to cross more space, which is being stretched as it expands, before their light reaches us, and thus that light experiences more redshift. Redshift, denoted as Z, can therefore be used to measure the distance to celestial objects with a known spectrum. And because light takes a finite amount of time to travel, this distance can be used to calculate how long ago these galaxies existed as we see them. JWST 14-0 has a redshift of Z equals 14.32, while the previous most distant galaxy, JWST 13-0, has a redshift of Z equals 13.2, which placed it as existing 400 million years after the Big Bang. Clearly, this newly found galaxy has absolutely smashed that record, with James Webb seeing back in time by another 100 million years or so. As JWST's collaboration team member Stefano Carniani of the Scuola Normale Superiore said, JWST 14-0 now becomes the archetype of this phenomenon. It is stunning that the universe can make such a galaxy in only 300 million years. Of course, Not everything about JD's JWST was immediately clear to the JD's team, and some elements could confuse our picture of the early cosmos. When it was first spotted, the primordial galaxy was so close to a closer foreground galaxy that the team suspected they could be celestial neighbors. This idea was dispelled in October last year, when the JD's crew spent 5 days performing a deep analysis of JD's JWST with NIRCam. The application of filters that are specifically tailored to identify early galaxies confirmed the extreme distance to JD's JWST. In the words of JD's team member and University of Arizona researcher Kevin Hainline, "We just couldn't see any plausible way to explain this galaxy as being merely a neighbor of the more nearby galaxy." The galaxy also surprised its discoverers because its light is even redder than expected. That is because the light from JADE's JWST is being reddened by dust within it that will become the building blocks of stars that will help this galaxy grow even larger. Another surprise was the discovery of oxygen in JD's JWST. Elements heavier than hydrogen and helium are forged by stars during their lifetimes and then distributed through galaxies when these stars explode. The observation of oxygen in this galaxy could indicate that at least one generation of stars has already lived and died in this very early galaxy. As JADE's researcher Jake Helton of Stewart Observatory and the University of Arizona explained, all of these observations together tell us that JADE's JWST is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe. Given the observed brightness of the source, we can forecast how it might grow over cosmic time. And so far, we have not found any suitable analogs from the hundreds of other galaxies we've observed at high redshift in our survey. Thus, Webb's newest discovery has profound implications for the predicted number of bright galaxies we see in the early universe. More fascinatingly, just a few days ago, astronomers using the Webb telescope have found what they say are 3 of our universe's earliest galaxies, spotted actively forming when the cosmos was just 400 million to 600 million years old. In Webb's images, this galactic trio resembles fuzzy red smudges feeding on nearby helium and hydrogen. Over millions of years, it is these elements that sustain such galaxies as they grow, helping to shape them into the familiar ellipses and spirals we see across the cosmos. According to study lead author Casper Elm Heinz, who is an astrophysicist at the Cosmic Dawn Center in Denmark, you could say that these are the first direct images of galaxy formation that we've ever seen. Whereas James Webb has previously shown us early galaxies at later stages of evolution, here we witness their very birth, and thus the construction of the first star systems in the universe. But while these stunning discoveries demonstrate that James Webb is reaching beyond its primary mission goals, they, like countless previous observations, continue to challenge our understanding of the universe.
The story of cosmology given to us by the Standard Model says that about 400,000 years after the Big Bang, electrons and photons found each other to create the first hydrogen atoms. Before this, they had been running free along with the photons that would soon become the cosmic microwave background radiation. Once this recombination into hydrogen occurs, the universe is largely composed of a fairly smooth gas of these atoms, with some helium around too, and the leftover background radiation. Now gravity can get to work within perturbations, small regions of overdensity in the hydrogen gas, and slowly collapse them to form the first stars. It is inside these first stars, which are formed only of hydrogen and helium, that nuclear fusion begins to forge all the heavy elements we know today. Elements like carbon and nitrogen play an important role in the story of galaxy formation. That is because these are the elements that can absorb heat from surrounding gas and emit photons that cool that gas. This cooling process will be critical in helping gas coalesce into galaxies. Eventually, these first-generation stars explode, and the resulting supernova seed the gas that surrounds them with heavy elements. Each supernova, along with black holes which are also forming, pumps ultraviolet radiation into the universe. This strips electrons from hydrogen atoms, making the universe more and more transparent to UV radiation. After the universe has run through a few generations of stars, there are enough heavy elements and UV radiation around to feed the formation of galaxies. Stars and vast quantities of gas collapse into gravitationally bound entities to pull these first galaxies together. This is a good story, and observations confirm key parts of it. The problem comes when it is placed within the cosmological context of the expanding universe. The standard model of cosmology gives astronomers a way to link the observed distances to objects, expressed in redshift, with their age relative to the Big Bang, expressed in years. Distances are measured by observation and cannot be tinkered with. Age, on the other hand, comes from a theoretical story. We take our models of an expanding universe, guided by Einstein's general relativity, and pour them into our understanding of matter, as expressed in the standard model of particle physics. These tell us how a distance, or a redshift, correlates with an age, a time since the Big Bang. So, what is the problem? Well, almost as soon as JWST, the James Webb Space Telescope, was turned on, it found galaxies at redshifts, and hence ages, much farther back than the standard model of cosmology predicts. Here's how the problem plays out. Within these images, we are looking very, very far away. Since looking to a particular distance means looking back in time, we are also looking very, very far back in time. But the universe has a beginning called the Big Bang. The age-redshift relation, which comes from the standard model, tells us how to convert an observed distance into a time after the Big Bang. But there seems to be a mismatch between how old these first galaxies appear to be and how long ago the age-redshift relation tells us they must have been formed. Well-formed galaxies are appearing too early for the story we have just told you to fully play itself out. The Big Bang model of cosmology shows us a universe that is evolving rather than static and eternally unchanging. It is not under question in any serious way. What these new JWST results do throw into question, though, is the story about the evolution that the standard model of cosmology tells us. That is what scientists say needs a big update, and the new data certainly provide a compelling clue that something might be amiss. The real question facing us is how much an update is needed. But that may be a question that will never be answered, because the most comprehensive thing about the universe is that it is incomprehensible. It once seemed that, for all its immensity, the cosmos could be understood through the application of a small number of rigid physical laws. Newton encapsulated this idea, showing how apples falling from trees and planetary orbits around our sun arise from the same force, gravity. This kind of radical unification of earthly and heavenly phenomena survives in modern teaching. All the innumerable molecules, atoms, and subatomic particles in the universe are expected to obey the same set of laws. Most of the evidence suggests that this assumption holds true, so it should follow that perfecting our understanding of these laws will resolve any remaining questions about cosmic history. Yet, this is a logical fallacy. Even if we imagine that humanity will ultimately discover a theory of everything, covering all individual particles and forces, that theory's explanation value for the universe as a whole is likely to be marginal. Over the course of the 20th century, even as particle physics revealed the secret of atoms, it became clear that behavior at the macro level cannot be understood by focusing exclusively on individual objects. Social instincts here on Earth provide a helpful example. Army ants, for instance, swarm to locate colonies of smaller prey, which they then devour. While swarming, they perform extraordinary feats of cooperation, using their bodies to smooth out the terrain or even build bridges over uneven ground. To human eyes, the collective behavior of the ants might suggest that an executive within the nest formulates strategies to reach prey efficiently, but there is no such decision maker. There are just lone ants following simple, unchanging rules, such as joining an ant bridge if there are many individuals pushing behind, and leaving the structure if no others crawl over it. The sophistication emerges from the sheer number of individuals following these rules. As physicist Philip W. Anderson put it, more is different. The solar system, seemingly the epitome of clockwork predictability, has an uncertain long-term future for this reason. In isolation, a single planet around a single star would orbit indefinitely, but in reality there are multiple planets, and they each tug, albeit very subtly, on the others. Over time, a series of tiny nudges can produce a major effect, one that takes an inordinate amount of calculation to predict. To an extent, computers can take on this challenge, simulating the collective result by adding the individual influences using fast and reliable arithmetic. The problem is that simulations disagree with each other. Some predict that the solar system is stable despite the continuing nudging, while others suggest that within a few billion years, Mercury might be coaxed onto a collision course with Venus, or even ejected into deep space. Solar system simulations disagree because no calculation can perfectly account for all the influences, and even the tiniest disagreement about the individual nudges lead to eventually a completely different outcome. It is an example of the phenomenon known as chaos, and it is simultaneously exciting and worrying. Exciting because it shows that planetary systems can exhibit much richer behaviors than the cold, lifeless law of gravity might suggest. Worrying because if even the solar system is chaotic and unpredictable, we might fret that attempting to understand the broader universe is a doomed enterprise. Consider galaxies, on average tens of millions of times larger in extent than the solar system, and lavishly varied in their shapes, colors, and sizes. Understanding how galaxies came to be so diverse requires, at a minimum, for us to know how and where the stars formed within them. However, star formation is a chaotic process in which diffuse clouds of hydrogen and helium slowly condense under gravity, and no computer is anywhere near able to track all the required atoms. There are around 10 to the power 57 in our Sun alone. Even if the computation were feasible, chaos would magnify exponentially the tiniest uncertainties, forbidding us from obtaining a definitive answer. If we were strict in sticking to traditional laws of physics as an explanation for galaxies, well, here is the end of the road. To fit inside computers, a simulation of a galaxy's formation has to lump together vast numbers of molecules, describing how they move en masse, pushing on each other, transporting energy, reacting to light and radiation, and so on, all without explicit reference to the innumerable individuals within. This requires us to be creative, finding ways to describe the essence of many different processes, allowing for a range of outcomes without obsessing over the detail, which is anyway unknowable. Our simulations necessarily rely on extrapolations, compromises, and all-out speculations developed by experts. The uncertain parts cover not just stars, but black holes, magnetic fields, cosmic rays, and the still-to-be-understood dark matter and dark energy that seemingly govern the overall structure of the universe. This will never result in a literal digital replica of the universe that we inhabit. Such a recreation is just as impossible as a precise forecast for the future of the solar system. But simulations based even on loose descriptions and best guesses can act as a guide suggesting how galaxies may have evolved over time, enabling us to interpret results from increasingly sophisticated telescopes, guiding us on how to learn more. Ultimately, galaxies are less than machines and more like animals, loosely understandable, rewarding to study, but only partially predictable. Accepting this requires a shift in perspective, but it makes our vision of the universe all the richer. However, we will never know everything about our universe. That is because the universe itself may be finite or may be infinite, but the part that's accessible to us is finite. Even with our expanding universe, even with all the galaxies and stars and planet and molecules and atoms and subatomic particles in it, there's only so much we can assess. And those limitations, the total number of particles and the total amount of energy available in the universe, means there's only a finite amount of information we can determine about our cosmos. For the first time, we can quantify that and begin to infer which things we might never understand. One of the ultimate questions about our universe is the question of where all this came from. When we discovered that the grand spirals in the sky were actual galaxies not so different from our Milky Way, all unto themselves, it paved the way for us to truly, for the very first time, understand the scope and scale of all that we can perceive. These distant island universes weren't contained within the Milky Way, but were collections of billions or even trillions of stars separated by millions or even billions of light years across the cosmos. When we found that the more distant a galaxy was from us, on average, the faster it appeared to be receding from our perspective, an intriguing possibility opened up, consistent with Einstein's general relativity. Perhaps the galaxies were not all speeding away from our location, but the fabric of space itself was expanding. If this were the case, then the universe should not only be expanding, but cooling, as the wavelength of light would be stretched to lower and lower energies as time went on. Moreover, we didn't just have to extrapolate forwards, but we could go backwards too, to a time where the universe was smaller in the past. If we looked in that direction, we'd find a universe that was denser, hotter, and more rapidly expanding and more compact. At early enough times, the universe would be so energetic that neutral atoms would be blasted apart, and even before that, individual atomic nuclei couldn't have formed. You see, there were a few major problems that arose if you tried to go all the way back that far. The universe wouldn't have expanded into oblivion or recollapsed almost immediately, never forming stars or galaxies, unless the initial expansion rate and the initial energy density were perfectly balanced. The universe would have different temperatures in different directions, something it was observed not to have, unless something caused it to have the same temperature everywhere. And the universe would have been filled with high-energy relics that had never been detected, a consequence of extrapolating back arbitrarily in the past. And yet, when we viewed our universe, it did have stars and galaxies, it was the same temperature in all directions, and it didn't have these high-energy relics. The solution to these problems was the theory of cosmic inflation, which replaced the idea of a singularity with a period of exponentially expanding space, and which predicted those initial conditions that the Big Bang on its own could not. In addition, inflation made 6 other predictions for what we would see in our universe. Number 1, a perfectly flat universe. Number 2, a universe with fluctuations on scales larger than light could have traveled across. Number 3, a universe with a maximum temperature that's not arbitrarily high. 4, a universe whose fluctuations were adiabatic, or of equal entropy everywhere. Number 5, a universe where spectrum of fluctuations was just slightly less than having a scale invariant, ns is less than 1, nature. And finally, number 6, a universe with a particular spectrum of gravitational wave fluctuations. The first 5 of them have been verified, with the 6th one still being sought. The next logical question about our origins, of course, then, becomes that of where did inflation come from? Was it a state that was eternal to the past, meaning that it had no origin and always existed, right up until the moment it ended and created the Big Bang? Was it a state that had a beginning, where it emerged from a non-inflationary state in space-time some finite time in the past? Or was it a cyclical state, where time looped back on itself from some far future state? The difficult thing here is that there's nothing we can observe in our universe that allows us to tell these three possibilities apart. In all but the most contrived models of inflation, and some of those we can rule out, it's only the last 10 to the power of minus 33 seconds or so of inflation that impacts our universe. The exponential nature of inflation wipes out any information that occurred prior to that, separating it from anything we can observe by, well, inflating it beyond the portion of our universe that we can observe. What we're left with is an observable universe that's huge, simply huge, 46 billion light years in radius, containing some 10 to the power of 12 galaxies, 10 to the power of 24 stars, 10 to the power of 80 atoms, and nearly 10 to the power of 90 photons. The total amount of energy in all the particles and all the empty space in the universe is somewhere around 10 to the power of 54 kilograms, including dark matter and dark energy. But those numbers, while astronomical, are finite and don't give us any information about what happened in the universe prior to the last tiny fraction of a second of inflation. We can do theoretical calculations to attempt to gain some insight, but they're all model dependent. With the exception of a few specific models that would leave observable traces in our universe, most don't, we have no way of knowing how, or even if, the universe got its start. Put simply, the universe may yet be infinite, but our knowledge of it never will be.
Despite that, for centuries, humans have been fascinated by the mysteries of the universe, driving us to venture beyond our planet and explore the vast space. Up to now, it could be said that humanity's journey into space has been one of the most awe-inspiring endeavors in our collective history. From the first tentative steps of Yuri Gagarin and Alan Shepard to the monumental achievements of the Apollo missions. Now the James Webb Space Telescope, space exploration, has captured the imagination of people around the world. But as we stand on the precipice of a new era of exploration, it's imperative to recognize why humanity needs to continue venturing into the cosmos. First and foremost, space exploration is crucial for the survival of our species. Earth, as vast and resilient as it may seem, is not immune to catastrophic events such as asteroid impacts, pandemics, or climate change. By expanding our presence beyond our home planet, we create redundancy for the human race. Just as biodiversity ensures the survival of species on Earth, spreading humanity across multiple celestial bodies ensures our survival in the face of existential threats. Moreover, space exploration drives technological innovation unlike any other endeavor. The challenges of space travel necessitate cutting-edge advancements in materials science, propulsion systems, robotics, and life support technologies. Many of these innovations find applications beyond space exploration, benefiting industries ranging from healthcare to telecommunications. The pursuit of space exploration pushes the boundaries of what is technologically feasible, propelling humanity forward into a brighter future. Space exploration also inspires future generations. The iconic images of astronauts floating weightlessly above the Earth or the breathtaking landscapes of distant planets serve as powerful symbols of human ingenuity and exploration. By capturing the imagination of young minds, space exploration encourages the pursuit of careers in science, technology, engineering, and mathematics. These fields are essential for addressing the complex challenges facing our world, from sustainable energy production to mitigating the impacts of climate change. Furthermore, space exploration offers unparalleled opportunities for scientific discovery. Whether studying the geology of Mars, probing the atmospheres of distant exoplanets, or unraveling the mysteries of black holes, space exploration expands our understanding of the universe and our place within it. Every new discovery opens doors to further exploration and raises new questions about the nature of existence. Beyond the scientific and technological benefits, space exploration fosters international collaboration and cooperation. The International Space Station stands as a testament to what can be achieved when nations set aside their differences and work together toward a common goal. In an increasingly interconnected world, space exploration serves as a symbol of unity, reminding us of our shared humanity and the importance of cooperation in tackling global challenges. Additionally, space exploration offers economic opportunities that extend far beyond the confines of our planet. The burgeoning space industry, encompassing satellite communications, space tourism, and asteroid mining, promises to create new markets and industries that will drive economic growth and prosperity. As access to space becomes more affordable and routine, the potential for commercial ventures in space will only continue to expand. In conclusion, the continuation of space exploration is not merely a luxury or a scientific curiosity, it is a necessity for the future of humanity. By expanding our presence beyond Earth, we ensure our survival, drive technological innovation, inspire future generations, advance scientific knowledge, foster international cooperation, and create economic opportunities. As we gaze up at the stars, let us remember that our destiny lies not only on this blue planet, but among the countless worlds waiting to be explored. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.